Welcome back to Calculus 1. In this lecture video, we're going to talk about the fundamental theorem of calculus. And I recall the previous recording, we talked about something called the definite integral. Okay, so this is what we talked about last time. The definite integral. If f is defined on a closed interval from a to b, the limit of the Riemann sum over the partition delta, okay, as the limit of the sum from I to n, f of c sub I times delta of xi, as the partition going to 0, okay. If that limit exists, then the function f is said to be integrable on a closed interval from a to b, and the limit is denoted by, okay, so the limit of Riemann sum, okay, as the partition approaching to 0, okay. What that means is, as you can recall, the width, okay, the width of the rectangles under the curve gets smaller and smaller and smaller. Okay, eventually that will actually lead us to what was called a definite integral from the integral of from a to b of my function. Okay, so we talked about the idea of area under the curve before and how they related. Okay, this is how area under the curve relate to the integral, is by thinking about as the length, the width of a rectangle gets so small, okay, eventually practically as the width approaching to 0, okay, that's practically a single c sub I that points on the curve. So if I can sum up all these points on the curve, okay, and take a limit of it, eventually that will be the same thing as if I will take an integral from a to b of my function f of x. And that's what we're going to do today, okay, and that is actually called the fundamental theorem of calculus. So what's going on here is, if a function f is continuous on a closed interval from a to b, then capital letter F here is an antiderivative of f on the interval. Then to find the area under the curve, we will just take an integral of my function f of x, and then we will evaluate it. Once I find the antiderivative, then we'll evaluate from a to b by substitute b into the antiderivative minus substitute a into the antiderivative, and we will subtract them. Okay, this is the fundamental theorem of calculus. So I'm going to bring this guy back. Okay, we actually did an example like this one way back in lecture video 5.1. And last time we did this example, x to the third power on the closed interval from 0 to 1 was use the limit process to find the region. So let me bring it back real quick. I can show you. Alright, this example. Use the limit process to find the area of the region. Okay. So what we did was find the width of the rectangles, b minus a divided by so many rectangles I'm going to do. Okay, my c sub I. Okay. A point on the ith interval. Alright, a point on the ith interval, and we end up using the right endpoint for those. And then we went through all this limit process, okay, and find out as n going to infinity, as I create more rectangle, eventually my area on the curve is 1/4. So we're going to do the same problem, okay, using integration. Alright, so let's take a let's find the integral of x to the third. if I use the power rule, that would be 1 over the exponent plus 1 here in the denominator as a coefficient times x to the 3 plus 1. Alright, I don't need to have the plus c, because when I do my evaluation, f of b minus f of a, the c will actually cancel out. And I'm going to evaluate it from 0 to 1. Alright, so this is basically 1/4 x to the 4th power evaluated from 0 to 1. So what that means is I will substitute 1 for x to the 4th power, and I will minus substitute 0 for the same function to the 4th power. So as you can see, 1 to the 4th power is still 1. 1 times 1/4 is 1/4. 0 times 0 to the 4th power is 0. 0 times anything still 0. So that's why my area under the curve is 1/4. Alright, so this part of the curve, okay, only from 0 to 1 of this cubic function is 1/4. Alright, so this is what we're going to do today. This is a mistake. Part B here is 1 to 2. Let's erase that. 1 to 2. Alright, let's try this one. Okay, so this is a parabola. Okay, I only want to find the area under the curve from 1 to 2. So since I'm subtracting here, I can split out this difference as 2 integrations. So this is going to be the integral from 1 to 2 of x squared dx in respect to x minus find the integral from 1 to 2 of 3 in respect to x. Alright, so this is going to be 1 over 3 x to the 3rd minus constant, we'll just add x to it behind the 3, and I'm gonna evaluate it from 1 to 2. Alright, so substitute 2 for x here. So that will give me 1/3 times 2 to the 3rd minus 3 times 2. We'll figure this out first. I'm going to put in a bracket, and then minus 1/3 times 1 to the 3rd minus 3 times 1. Alright, so if you put all the stuff in the calculator, your answer negative 2 over 3. Okay, there's negative 2 over 3. Let's try another one. Evaluate from 1 to 4. Okay, 3 times square root of x. So just like in a previous lecture video, we can factor out this 3, and I'm only gonna integrate the square root of x. Square root of x is the same thing as x to the half power. So all we're doing so far is find the integral first before I substitute in, and then find the area under the curve. So this is going to be 3 times, okay, bring the half to the denominator plus 1, and x to the half plus 1, and I'm going to evaluate it from 1 to 4. Alright, so this is going to be 3 times, let me put this in the bracket because this 3 is times this whole thing. So this is going to be 3 times 1 half plus 1 is 3 half. 1 divided by 3 half is 2/3. X to the 3 half. 1 half plus 1 is 3 half. evaluate it from 1 to 4. Alright, so I'm going to substitute 4 into this for x. So that will be 3, this 3 times 2/3 times 4 to the 3/2 power. Okay, minus, so we'll put this in the bracket, minus the same 3 times 2/3 times 1 to the 3/2 power. Alright, so if you put this in the calculator, then put that part in the calculator and subtract them, so then that will give you area 14. Alright, so what is so-called the fundamental theorem of calculus, okay, is really about finding the integral, okay, of your function, and we evaluate it, okay, in the on the closed interval, okay, from a to b. Alright. Now, the next thing I want to kind of talk to you about, okay, it's called the mean value theorem for integrals. Okay, recall that the area under the curve of an inscribed rectangle is less than the area of a circumscribed rectangle. Okay, so you can recall when we talk about area under the curve, inscribed rectangles are rectangle drew that's under the curve. Okay. The circumscribed rectangle is where we drew it out a little bit. Okay, where we drew it out a little bit. Something like that. Okay, inscribed will be the one that's inside of it, which is would be this way. So that's what's the difference between the right point and left. That's when we talk about the right endpoint and the left endpoint. Alright, so we know the circumscribed rectangle has more area than the inscribed rectangle. Now, by the mean value theorem for integral, it states that somewhere between the inscribed and circumscribed rectangles, there is actually a rectangle whose area is precisely equal to the area under the curve. Okay. There's a rectangle whose area is precisely equal to the area, okay, under the curve. So let's say here, okay, I will pick a number c somewhere between the interval from a to b. I know that for my limits, okay, when the limits as the partition going to 0, okay, I can pick a c sub I times the width, okay, and I can add them all up, okay, on this curve, and then the limits as the partition going to 0, that will actually give me the area under the curve. So what my drawing here is trying to show you that you got two types of rectangle, inscribed and circumscribed. They're somewhere in the middle, okay, which is where the C is located. Okay, if I will pick this number C and draw a rectangle here, the area under the curve, okay, this area under the curve will actually equal to this picture here. There's a rectangle whose area is precisely equal to the area under the curve. So this picture here is all the area under the curve. In this part, this picture here has a highlight yellow just inside the rectangle. So part of the space I shaded, okay, is actually above the curve. So circumscribed. This is a circumscribed rectangle. Okay, this is more like an inscribed rectangle here. Eventually these two areas will actually equal to each other if I can pick this number C. Okay, so the height will be the f of c. Okay, the mean value theorem. The word mean is referring to halfway. So this line right here, okay, this line here is actually your height. Okay, from C to B is your width. So this f of c is actually my height for both pictures. So somewhere on this curve, okay, if I can have a rectangle, I can draw a rectangle, okay, where if I can find that number c and I can evaluate at f of c, the area under that rectangle is going to be the same as the entire area under the curve. Okay, very interesting. So here is what the theorem says. If a function f is continuous on a closed interval from a to b, then somewhere there exists a number c such that the integral of the function from a to b will be f of c times b minus a. Okay, so f of c is your height. Your entire width is from a to b. So if I want to find the area of just this part of the rectangle, of course, that will just be the interval from c to b. But if I'm talking about the interval from entire a to b, okay, the entire interval from a to b, this whole thing underneath the rectangle, okay, that area, just like this picture here on the right, will equal to the area just under the curve. Alright, so what this equal to is saying is you take the height, okay, times the width. So this f of c is referring to the average value. Okay, this f of c is referring to the average value of f on the interval. Okay, this line, this dash line on top is the average value. So we are taking the average value, okay, times the entire width of the interval. And if you're not quite sure what I mean by this average value, just remember now, at this point where I pick the c at, the x value is c, the y value is f of c. Okay, so if I go straight back to the y-axis, this is actually your f of c right here. So this y value, okay, is the average value, is what we so-called the average value. Okay, and this average value is referring to the height as well. A little bit confusing. Now, if I can manipulate this equation, okay, to get f of c by itself, all I'm going to do is divide both sides by b minus a, and then we get this number. Okay, so to find the average value, okay, to find the average value, is 1 divided by b minus a and times the integral of from a to b of my function. Alright, very, very neat idea. If you think about some of these graphs that we drew before from the area under the curve, where we drew a lot of rectangles, using, just look at this picture for example. Okay, for the interval from 0 to 2, I can actually create some sort of rectangle. Okay, and I'm gonna pick a number c. I'm gonna pick a number c somewhere on this there's a number c on the rectangle. Alright, where the area under the curve here is gonna be the same as the entire area. Oh, excuse me. Let me draw it this way. If I pick the C right here, then this part is my f of c. And I'm going to draw this rectangle all the way out here to my ending at 2. Alright. So basically, everything I highlight in yellow is area under the curve. Okay, if I can find this number C, this area under the curve will equal to the area of the entire rectangle. Okay, where the height will be f of c. That's called the average value. Very, very interesting. Somewhere along this line, somewhere along this curve, all the area under the curve is actually equal to an area of a rectangle, and where that value, okay, that's c, and f of c, create this area under the curve is the same as the area under the curve. Okay, very, very unique, interesting idea. Alright, so let's find the average value of the function. Okay, let's find the average value of the function over the given interval. Now I'm gonna show you how that picture works. Okay, so let's find this average value. So here's my function. To find the average value, f of c, it's going to be 1 over b minus a, 4 minus 1, times the integral evaluated from 1 to 4 of my 3x squared minus 2x in respect to d sub x. So this is going to be 1/3 times, I'm going to go ahead and figure this out, okay? Alright, 3 times, okay, factor of this 3 to the front of the integral. 1 over, bring the exponent to the bottom of my fraction, plus 1, x to the 2 plus 1, minus, factor of this 2 to the front of the integral, times 1 over, the exponent here is 1, so that's 1 plus 1 times x to the 1 plus 1. We're going to evaluate from 1 to 4. So this is going to be 1/3 times, let's clean this up. This is 3 down here. That 3 and that 3 will cancel out. So that's leave me x to the 3rd power minus. Second term, 1 plus 1 is 2. 2 and that 2 reduce. So that just be x to the 2nd power. Okay, evaluate from 1 through 4. Alright. So this is going to be 1/3 times. Okay, I'm gonna substitute 4 in here. So that will be 4 to the 3rd power minus 4 squared. I'm gonna minus, okay, substitute 1 for x here, so that'll be 1 to the 3rd minus 1 squared. Alright, 1 to the 3rd is 1. 1 squared is 1. 1 minus 1 is 0. So all these terms are going to become 0. So that just leave me with 4 to the 3rd minus 4 squared, which is 48. And that 48 divided by 3, which is 16. Alright, so my average value is 16. My average value is 16. So if you look at this process, okay, if you look at this process, let's say I do not have this 1 over b minus a part. If I exclude this part out, this part only is the area under the curve. So what that tells me is before I divided by 3 at the end here, the area under the curve was 48. Okay? The area under the curve was 48. By dividing by 3, it allowed me to find the average value. So, you imagine this whole yellow part under the curve is 48. Okay, that's 48 already. So if you think about over here, okay, this whole thing under the curve, this whole thing under the rectangle is also going to become 48. Okay, based on what the mean value theorem says. So if we take the average value f of c times b minus a, which is 4 minus 1 is 3, 16 times 3 will actually give me my area under the whole rectangle, which is the same as the area under the curve. Okay, so the only difference between this picture and that picture is, again, this yellow part is under the rectangles only. This part is actually under the curve. So if I can, so we can find, so there exists a number c here, where if we can find the, if there exists a c, then we can figure out what f of c is. Okay, once I can find f of c, okay, I can times the b minus a. That will give me the area under the curve. And we kind of show it right here. So after all, the area under the curve is 48. So is the area of this big rectangle, and they are equal to each other. Okay. Alrighty. So that's the mean value theorem for integrals. Very, very powerful theorem. And of course we can find c as well. We can actually find c if we just manipulate it a little bit. Alrighty. Let's take a look at what we so called the second fundamental theorem of calculus. Okay. Alright, this is a little bit strange. We've been evaluating our integral from a to b in respect to x. So the definite integral as a number. My final answer is always going to be a number when I take an integral of my function and evaluate from a to b. So this function f is actually a function in respect to x. Now sometimes this comes up, the definite integral as a function of x, where I actually gonna evaluate from a to x. Okay, my integral is gonna be from a to a particular number. Okay, from a to a variable x. Okay, whatever that x is. But my function that I'm evaluating is actually not in terms of x, because that would cause some confusion with the variables. So I'm gonna use a variable t. So my function f here is a function in respect to t. Okay, so basically what I have here is I have a all the way down to a x. Okay, that's my closed integral. Alright, so if I have this function right here, alright, this function will be f of t. Alright, so let's do the same thing as we've been doing, okay? Except I'm going to use x in a minute. So let's find the integral of cosine of t in respect to t. Cosine of t, I believe, is sine of t. And I'm going to evaluate from 0 to x. So substitute x for t, that would be sine of x minus sine of 0. And sine of 0 is 0, so that means my answer will only be sine of x. Alright. So this is the weird part about it. The second fundamental theorem for calculus says this. If a function f is continuous on the open integral from a to b, then for every x in the interval, it turns out the derivative in respect to x of the integral from a to x of my f of t will actually equal to f of x. Okay, will actually equal to my original function f of x. Because come think of it, if I ask you to take an integral, okay, of cosine of x dx, that will eventually become sine of x. Okay, that's what this thing is trying to tell you. So this is how it goes. I'm gonna show you how we derive this. Okay, let's see if it makes sense. All right. Originally, this thing is an antiderivative. So derivative of the in respect to x of antiderivative in respect to x is equal to, okay, what was my antiderivative here? My antiderivative turns out to be sine of x. My final answer was sine of x. Okay, so this was the f of x. This is the antiderivative, which is equal to that, which eventually end up to be sine of x. Alright, so if I want to take derivative of my antiderivative, which will eventually become a sine of x, okay, which is the same as derivative of my integral from 0 to x of cosine t dt. Okay. Which eventually will actually give me cosine of x. Which actually give me cosine of x. Think about it. My answer here is sine of x. If I take a derivative of sine of x, if I take a derivative of a sine, it will actually give me cosine. Okay. And that's what second fundamental theorem calculus is telling us. Alright. If I would take a derivative of an antiderivative, I will get my original function back. Alright. And I can show you with another example as well. Right, so you almost have to look at it, from a different perspective. Derivative of the antiderivative got to kind of like cancel each other out. So that, of course, you're going to end up with the original function, which the original function is cosine of x in respect to x, okay, or just cosine x as well. So this answer equal to sine of x is referring to the antiderivative. If I take a derivative of the antiderivative, that should bring me back to the cosine of x. All right, let me show you. I'm gonna skip over this problem. I'm gonna come down here, do this one. Okay. So this is not cotangent of t. This is cosine of t. COS. I have a typo here. T dt. Okay, check this out. All right, I'm gonna go ahead and find. I'm gonna do what the problem asks me to do. Okay, find the antiderivative. But this time, it's actually pi over 2 to x to the third power is what I'm going to evaluate. Alright, so integral cosine of t, excuse me, dt. Again, that will give me sine of t. Evaluate from pi over 2 to x to the third. this is going to be sine of x to the third, substitute t for x to the third, minus sine of pi over 2. Alright. Pi half is 90 degrees. So sine of 90 degrees is 1. So this is going to be sine of x to the third minus 1. So this is the antiderivative. Okay. This is my calculator F. Alright. Now, if I will take a derivative of this, if I will take a derivative of my sine to the third minus 1, okay, if I will take a derivative of my antiderivative, okay, this time it does not really bring me back to cosine of x, because this is to the third power here, so the answer is slightly different. Derivative of sine to the third, excuse me, derivative of sine x to the third power. Alright, just think about sine u is equal to cosine of u times u prime. So this is going to be cosine of x to the third times u prime. This is my u, so that will be 3x squared. Okay. Alright, then negative 1 drop off when I take a derivative. So this answer here will be the derivative. Okay. This answer will be the derivative of the antiderivative. Alright, and this answer at sine of x to the third minus 1 is the antiderivative. There you go. So that means if I would take the derivative, okay, for my integral of sine of fx, derivative of the antiderivative. So what was my antiderivative turn out to be? My antiderivative was, final answer for the antiderivative was sine x to the third minus 1, which is equal to, okay, the derivative of that same integral. You know what? I'm going to do it this way. I'm going to set derivative of the f of x, and where f of x was equal to this thing up here, which is the integral from pi over 2 to x to the third power of cosine t dt, and that turned out to equal to the sine of to the third minus 1, which is end up to be cosine x to the third times 3x squared. There you go. So this part is the original f of x. Okay. Derivative of the antiderivative will equal to the original function f of x. So this one is a little bit more complicated. Alright, let me do this one up here. Okay, we're going to see it better. Integrate to find f as a function of x, then we're going to find f prime, derivative of the antiderivative. So we're going to split these three. Okay, it has three separate integrals. So bring the exponent down to the denominator. That's 1 over 4, because the exponent got a plus 1. T to the 4 power minus 4 times This is 1. Bring the exponent down, plus 1, that's 2. And if I reduce it, that would be 2t squared minus 5t. And I'm going to evaluate it from 2 to x. Okay, check this one out. This one is actually easier than the other one. Alright, this is a lot of work. We're going to substitute x for all these t right here. So that gives me 1/4 x to the 4th. 2 times x squared minus 5x. Okay, all these guys will subtract. All these guys will subtract. Now I'm going to substitute 2 for all these t. So that's 1/4 times 2 squared. 2 to the 4th minus 2 times 2 squared minus 5 times 2. Okay, so all these guys here in the second bracket will actually become 10. So minus 10, that means this function is the antiderivative. Okay, this is the antiderivative, which is calculator f of x. Okay, so that's the first part of this problem. Now f prime of x. So what happens if I take a derivative of my antiderivative? I bring down the 4, right? Derivative of this whole thing, bring down the 4. So 1/4 times 4 would just be x. Subtract the exponent by 1, that's 3. Bring down the 2. That'll be 2 times 2 is 4x, because the exponent dropped down by 1, minus 5, because negative 5x will just be negative 5. There you go. And this right here is the f of x, which is, oh, look, just like these, except these guys are in terms of t. Alright, so it kind of makes sense that derivative of the antiderivative is the same as taking a derivative of the integral, okay, from 2 to x of my function in terms of t to the 3rd minus 4t minus 5 dt, which eventually is saying taking a derivative of my antiderivative 1/4x to the 4th minus 2x squared minus 5x minus 10. So derivative of the antiderivative will keep bringing me back to my f of x, x to the 3rd minus 4x minus 5. And that's my f of x. Second fundamental theorem of calculus. Okay, sounds like a no-brainer. Okay, in a way it sounds like no-brainer. But don't be mistaken. I'm not switching variables from t here to an x. Okay, that's not how it really works, because as you can see from this example, what happens if I want to evaluate to x to the 3rd power? Okay, then what we notice here is it's not simply switching from this t to an x as a final answer. Okay, it doesn't work like that. For a simple problem, yes. Okay, for more complicated problem, we actually need to figure it out. Alright. Alright, that will conclude this lecture video presentation. Thank you for watching. In the next video, we will talk a little bit about more integration.